All right, let's talk about binary search. If you've ever flipped through a phone book to find a name, you've basically used it. It's one of those classic fundamental algorithms, a super fast way to find an item in a sorted list. The idea is simple. You check the middle, you throw half the list away, and you just keep doing that. It's incredibly efficient, and on the surface, it seems like a total piece of cake.
And the logic, it's just beautiful, right? You start with your sorted list, you jump right to the middle. Is the thing you're looking for bigger or smaller? Whatever the answer, you now get to completely ignore half of the entire list. You just keep cutting the problem in half, again and again, until you've completely zeroed in on what you're looking for. It's a perfect example of a divide and conquer strategy.
I mean, seriously, what could possibly be simpler than that? It just feels like pure common sense. But this is exactly where the story gets really, really interesting. That right there, that's a warning from Donald Knuth, an absolute titan in the world of computer science. So when a guy like that says the details are surprisingly tricky, you should probably pay attention. This simple idea is hiding a whole lot of trouble. And if you need proof, just look at this number. John Bentley, another giant in the field, once wrote that he gave binary search as a problem to professional programmers. We're talking people at places like Bell Labs, IBM, and a staggering 90% of them got it wrong. Their code had bugs. These aren't students, these are seasoned pros. So what in the world is going on here? Well, the history of the algorithm tells the tale. It was first described way back in 1946. But it took 16 years before a completely bug-free version was finally published. And even then, the story doesn't end. Around 2006, a really subtle bug was found in Java's standard library implementation of binary search. It had been hiding there in plain sight for almost a decade, affecting code used by millions of developers. So look, the point is, this isn't about being smart. It's about being careful, because this thing is subtle. So let's do a little autopsy on this simple algorithm and see exactly what makes it so hard to get right. The mistakes usually fall into just a few categories. You've got your classic off by one errors. They're the real killer, where you get your boundaries wrong by just one little number. Then there's integer overflow, which can totally crash your program if the list is big enough. And of course, infinite loops, where your code just gets stuck running forever. And then there are the edge cases, like what happens with an empty array, or if your target is at the very beginning or the very end. That's where things really tend to fall apart. Let me show you a perfect example. How do you find the middle of your search area? Well, the obvious way is to just add the left and right pointers and divide by 2. Makes perfect sense, right? But there's a safer way, which you can see on the right. And the tiny difference between these two lines of code, that was the source of that infamous bug in Java. So here's the hidden danger: integer overflow. If your array is absolutely massive, the sum of left plus right can actually get bigger than the maximum number a standard integer can even hold. When that happens, the number wraps around, becomes negative, and boom, your program just breaks. The safer way avoids this entirely because it calculates the distance first. It's such a tiny change, but it makes all the difference. And here's the other classic trap. When it's time to shrink your search space, how exactly do you update your left and right boundaries? If you're not super precise, like if you say left equals mid when you really should have said left equals mid plus 1, you can get into a situation where the search space just stops shrinking. Your algorithm gets stuck, checking the same few elements over and over and over again forever. Okay, so we've seen all the ways this can go wrong. How do we make sure we get it right every single time? Well, the answer isn't about memorizing lines of code. It's about building a solid mental model that stops these bugs before they can even happen. The real question we have to ask is this: how can we absolutely guarantee that our logic is sound? How do we prove to ourselves that every single step we take is getting us closer to the answer without ever accidentally throwing the right answer away or getting stuck? And the answer comes from this really powerful idea in computer science called a loop invariant. You can just think of it as a promise. It's a rule that your code swears it will uphold. It's true before the loop even starts, and no matter what happens inside that loop, it's still true after every single pass. It's a rule that never breaks. So what's our promise for binary search? It's actually really simple, but it's profound. The invariant is, if the target we're looking for exists at all, then it is guaranteed to be within the left and right boundaries we are currently searching. Our entire goal is to make that search window smaller and smaller without ever breaking that promise. Okay. That's a great theory. But how do we actually translate that safety rule into code that just works? How do we build an implementation where the logic is so solid that it's practically impossible to make one of these classic mistakes? This is the ultimate template for a bug-free binary search. Let's walk through it because every single line is there for a very specific reason. First, we set our boundaries to cover every possible answer. Then, the heart of it. The loop condition is while left less than right. This is so important. It guarantees the loop has to end because left and right are always getting closer. Now look inside. If our condition is true at the midpoint, that means mid could be our answer, or maybe an even better answer is to the left. So we can safely shrink the boundary by setting right equals mid. But if the condition is false, we know for a fact the answer has to be in the upper half. So we set left equals mid plus 1. That tiny plus 1 is the secret sauce. It's what ensures we always make progress and never get stuck. When that loop finally stops, left is your answer. This structure basically forces you to keep your promise.
And once you mastered this template, you unlock the true power of binary search. Because it turns out, it's not just for looking up a number in an array. It's a powerful problem-solving framework that can do so much more.
The big insight is that a huge number of really complex problems can actually be boiled down to finding a transition point, the very first moment that some condition switches from false to true. So imagine a long line of falses followed by a long line of trues. Binary search is the absolute best tool for finding that exact spot where they meet. And this table just lays out the difference perfectly. On the left, you've got your traditional binary search, which is just looking for an exact match. But on the right, you have this condition-based search, the one our template is built for. And it is so much more versatile. It's not just looking for a value, it's designed to find the index of that boundary, which is exactly what you need to solve a whole class of really tough problems. So after all that, what's the big takeaway here? What's the one thing we really need to remember about this deceptively simple algorithm? We've really been on a journey, haven't we? We started with this idea that felt like total common sense. Then we found out it was a minefield of bugs that has tricked the best programmers for decades. We figured out exactly where those mines are hidden. And finally, we armed ourselves with a mental model and a template to get through it safely every single time. And that right there is the core lesson. The goal was never to just memorize some code. It's about building a robust mental model. Understanding the why behind the code, that concept of the loop invariant, that's what takes you from someone who might get it right to someone who basically can't get it wrong. And that leaves us with one last big question. Binary search taught us that even the simplest seeming ideas can hide some really deep and tricky details. It kind of forces you to ask, what other simple ideas out there, maybe in our jobs or just in our lives, are we totally taking for granted? And what might we find if we just dared to look a little bit closer?